Welcome back everyone. In this lecture I will introduce the notion of tensor products. So, I am not going to assume you know everything about tensor products. So, I am going to actually start with the construction and then slowly build up how to define the tensor product of vector spaces. So, from there we will actually go from vector spaces to representations. Okay, so let us actually start with two vector spaces. Let us call them V and W. So, let us say V and W to be vector spaces defined over complex numbers. So, for simplicity we can just work with 5 dimensional vector spaces, but tensor products are actually defined in very generality. So, I am not going to do it in that generality. I am going to make some assumption. For example, I am going to assume our field to be complex numbers and so on, but from the definitions you can see that one can actually define the notion of tensor products in very generality, like over any field and for any dimensional vector spaces, or even more like for any modules over some commutative rings and so on. Okay, so let me actually define the tensor products using the universal property. So, the tensor products, so they are very much related to this bilinear maps. So, all of you of course know the definition of bilinear maps. So, we call a map from V cross W to Z. So, let us call it F. So, V cross W to Z, and this is called bilinear map if it is linear in both variables. If it is linear in both variables. So, this is the definition of bilinear map. So, for example, in the first variable, like if I take f of v 1 plus alpha v 2 w. So, then we get exactly equal to f of v 1 w plus alpha f of v 2 w, and this is true for alpha 1 alpha sorry this is true for all v 1 v 2 in V and w in W and alpha in C. Okay. So, similarly one can define linearity in the second variable. So, that actually defines what is called bilinear map. So, now what we want to do? We want to actually get a universal vector space that actually extends all possible bilinear maps from V cross W to any given vector space Z. Okay. So, this is the question or the universal property. So, the universal property of the tensor products is given as follows. So, let us say I have a bilinear map from V cross W to Z. So, let us call it F. So, F is a bilinear map, and now what we want to do. So, let me put a box here. So, we want to actually construct a space which is universal in the following sense. So, we denote that space by V tensor W. So, we want a space V tensor W such that we also want some natural map from this V cross W to this V tensor W, again given by bilinear map. Let us call that map iota. So, this is also a bilinear map. So, this iota is fixed. So, this is indeed fixed. So, now given this bilinear map F, what we want? We want that some extension of this F as a linear map from V tensor W. So, we want to enlarge this given V and W and then produce very big vector space V tensor W, and we want to think as bilinear maps as linear maps from this constructed bigger vector space V tensor W to Z. So, that means, so given this F, we want a extension F bar such that this diagram indeed commutes. So, what is the meaning of the diagram commutes? So, when I look at this map F, which is actually obtained by the composition of these two maps. So, basically first you apply iota and then you apply this F bar. So, this is the meaning of commutation of this map. So, let me write it clearly. So, given F, which is a bilinear map, there exists unique F bar from V tensor W to Z, which is a C linear map. So, everything is C linear or C bilinear such that this relation F equal to F bar composition iota actually holds. So, the diagram above diagram commutes. So, we want such a pair V tensor W comma iota. So, that is indeed called the tensor product, but it is understood that this iota is already there. So, we just simply call V tensor W to be the tensor product of V and W. So, like I said, we want to think all bilinear maps as linear maps from V tensor W to G. Okay. So, how one actually constructs? So, if we think about it, so let me actually work backward little bit. So, let us understand this map iota. So, the iota is a bilinear map from V cross W to V tensor W. So, now if we think about it, we can actually denote the image of the pair V comma W as just V tensor W. So, these are called simple tensors. Indeed, the simple tensors, they are going to span this V tensor W. So, now, so what is the meaning of iota being bilinear? So, if we take V 1 plus V 2 comma W, so then that is going to be mapped to V 1 plus V 2 tensor W. And you can see that iota being bilinear, that simply actually translated as follows. So, if this is iota of V 1 plus V 2 comma W, then this is going to be exactly equal to iota of V 1 comma W plus iota of V 2 comma W, which is exactly equal to V 1 tensor W plus V 2 tensor W. So, indeed, so we want this linearity in the first coordinate. So, that is what translated here, and if we put alpha here, so we get alpha here and then alpha outside. So, you can see that. So, we have this following important relation V 1 plus alpha V 2 tensor W should be equal to V 1 tensor W plus alpha V 2 tensor W. Similarly, if we are going to use the second coordinate, we get V tensor W 1 plus alpha W 2 is going to be exactly equal to V tensor W 1 plus alpha V tensor W 2. So, these are some important necessary conditions to define the tensor product. Okay. So, this actually motivates us to do the following construction. So, here is the construction. So, we use the quotient space construction. So, what we are going to do? We are going to take the free vector space spanned by V cross W, and then we are going to demand these relations are there in our space. So, we take this free vector space spanned by this V cross W. So, that means, so the elements V comma W, V in V and W in W, this entire set, this is going to be a basis for this capital L. And now what are all the relations? So if we take these relations and then translate them, so the relations are going to be, so this is a subspace spanned by the following elements. So let me list it here. The first set of elements is V1 plus V2 comma W. So this is going to be equal to V1W plus V2W. So in the tensors you can see that, so you have to read it as this is going to be the image going to be V1 plus V2 tensor W. So that means, so this is minus V1 comma W minus V2 comma W, we want to be actually equal to 0. So that is the relation that actually comes from when we take this alpha to be 1. And similarly, if we take V W1 plus W2, so this should be equal to V tensor W1 and then plus V tensor W2. So that means you have to subtract these two. And similarly, the third relation SV comma W minus S times V comma W. Fourth relation V comma SW minus S V comma W. And all these are true for all V, V1, V2 or comes from V, S is coming from complex numbers, and then W, W1, W2 they comes from capital W. And we take this space capital L and then go modulo R. So that is our tensor product. So V tensor W over C is defined to be L modulo R. So this is the definition of the tensor product. So we can directly check that we have the universal property. So note that, so we have a natural inclusion from V cross W to the free vector space L, because this is indeed spanned by V cross W. So the map V comma W mapping to V comma W in the basis, so that is going to give us inclusion, and we have this natural quotient map, so which is goes from L to L modulo R. So the composition is what the iota, the natural map. So the iota is a map from V cross W to this V tensor W, which is given in this diagram. So now note that naturally V comma W is mapped to the image, we will denote it by the simple tensors V tensor W. So this is just a definition of V tensor W. So it is that corresponding V comma W plus R coset that is there in L modulo R. So now it is not difficult to actually check that V1 plus V2 tensor W is going to be exactly V1 tensor W plus V2 tensor W. So I will leave it to check this iota is indeed bilinear map. This iota is indeed bilinear map. And note that clearly we have the following universal property that we actually promised. So if we take this V cross W, from here we have L, we have this quotient L modulo R, and now given this bilinear map F from V cross W to Z. So this is let us say given bilinear map. So what we can do, we can extend this map to L to Z, because any set map from V cross W to Z can be extended. So treat this F as set map. So then this F can be extended to L uniquely. So there exists unique extension, let us call it F bar, or let us say call it F tilde, F tilde, so that this diagram commutes. So this is the inclusion iota, and we have this f tilde. So, what is this f tilde? F tilde is just linear extension of f. So, then we have this f tilde which is from L to Z, this is C linear extension of f. So, now it is easy to see that R is indeed contained in the kernel of f. So, this is contained in kernel of f tilde. So, what is the meaning of that? So, when you apply f tilde, so note that what is R? R is generated by these elements. So, let us actually verify the first relation. So, f tilde of this is supposed to be 0, and that actually immediately follows from the fact that f is being bilinear map. So, let us calculate. So, f tilde of V 1 plus V 2 comma W minus V 1 comma W minus V 2 comma W. So, this is an element in the free vector space L, and the way f tilde is defined. So, since f tilde is linear extension of f, this is going to give us f of V 1 plus V 2 comma W minus f of V 1 comma W minus f of V 2 comma W. But note that f is being bilinear, this is exactly 0. So, that means, so this element is indeed inside the kernel of f tilde. So, that means, so other relations I will leave it to you to check, the R is contained in kernel of f tilde. So, that means the map f tilde naturally factors through L modulo R. So, you get this factorization. So, which we will call it f bar, and f bar of x plus R is defined to be just f tilde of x. So, this is how the factorization work such that this diagram commutes. So, now note that, so this map is nothing but iota, and since this diagram commutes, so all the diagrams actually commute. So, that would imply that we have this following map. So, from V cross W to this V tensor W, which is L modulo R, which is iota, and then you have this f bilinear map from V cross W to Z. So, then you have this natural extension called f bar such that this diagram actually commutes. So, this is something easy. Now, since this iota is bilinear and f bar is linear, so since iota is bilinear and f bar is linear, so that would say that the composition is indeed bilinear. So, iota composition f bar is bilinear, and you can see that so V comma W will be mapped to V tensor W here, and then V tensor W is indeed mapped to f of V tensor W. So, that means this is going to be exactly equal to f. And since the simple tensors that actually spans, so V tensor W indeed spans V tensor W. So, that would imply that f bar is indeed unique. Okay. So, this proves actually the universal property of this V tensor W. Okay. So, what are some basic properties of this tensor product? Maybe like using the universal property, you will be able to prove that we have a nice basis of this tensor product using the basis of V and W. So, maybe let me leave it as exercise. So, let us say, so I am going to assume that all are finite dimensional. So, let us fix V 1 etcetera V n to be basis of V and then W1 etc. Wm to be basis of W. So, from this you can get that Vi tensor Wj, where I is running from 1 to n and j is running from 1 to m. So, this is a basis of V tensor W. So, indeed it is not very difficult to prove, it actually spans, because the simple tensor spans V tensor W. That will follow from the fact that V comma W, where V runs over capital V and W runs over capital W, is a basis for L. So, V W, V in V, W in W. So, this is indeed a basis for L. So, that would imply that the image V tensor W, V in V and W in W. So, this is going to be a spanning set for the quotient. So, that is easy to see. So, from that you can easily prove that this indeed form a spanning set, and with some extra work you can easily prove that this is indeed linearly independent. So, I will leave it to you to check. Okay, so, we have this important basis, and we also have this associativity and commutativity of the vectors tensor product as vector spaces. So, here is the commutativity. So, we know that V tensor W is indeed naturally isomorphic to W tensor V, and the simple tensor V tensor W is indeed mapped to W tensor V. Okay, let me just demonstrate how to actually prove this, because this is what helps us to understand how to work with the tensor product. So, in case if we are interested in actually constructing a map from the tensor product to any other vector space, so we need to use the universal property. So, basically we take V cross W and then the targeted vector space being this W tensor V. So, we can simply map V comma W to this W tensor V. So, that is going to define a bilinear map from V cross W to W tensor V. That is not hard to check. So, now we have this iota which is a map from V cross W to V tensor W. So, then this map, let us call it F. So, this is going to extend to this V tensor W to W tensor V. So, you get this unique extension F bar such that this diagram comes. So, that means when you take this V tensor W, you can see that this is naturally mapped to W tensor V. And similarly, you can construct the inverse from W tensor V to V tensor W, and using the universal properties you can check that that map is indeed inverse of the map F bar that we constructed. Okay, that is how you prove any isomorphism between the tensor products or existence of any map from tensor product to some other vector space. So, here is the associativity. So, which is again easily proved using the universal property. So, maybe I will leave it to you to check. So, if you take 3 vector spaces U, V and W, U tensor V we can form, and then we can actually take tensor with W, and naturally this will be isomorphic to U tensor V tensor W. So, this is what associativity says, and all these isomorphisms are vector space isomorphisms. So, this is also as vector spaces, and here this also as vector space. So, how the isomorphism is given? So, again you can define it on the simple tensor U tensor V tensor W is indeed mapped to U tensor V tensor W. So, this is the isomorphism that is given. And we can also talk about tensor product of maps. So, here is a simple exercise. So, given let us say 2 maps F from U to V and then G from W to Z. So, from this we can prove that there exists a map which is a linear map from this tensor product U tensor W to this V tensor Z. So, let us call that map F tensor G, linear map such that the image F tensor G on the simple tensor U tensor W is indeed mapped to F of U tensor G of W. Okay. So, this is how the map indeed the tensor product of two linear maps are defined. Okay. This again you can use universal property to prove that. The key thing about this tensor product of linear maps is that we can talk about the matrix of this tensor product of maps, and that is indeed related to what is called Kronecker product of matrices. So, let me recall what is the Kronecker product. So, let us fix some dimension of the matrices. So, let us call A to be the matrix Aij, let us say of m by n size, and then let us say B to be the matrix BLK, so which is of size P cross Q. So, now the matrix A tensor B is defined to be this augmented matrix. So, you take the size m p times n q. So, where what we do, we just take the matrix B and then multiply the entries of A with that. So, we replace this first block to be A11B and then second block to be A12B and so on, then A1NB etc. Then here we get AM1B etc. AMNB. So, basically we take this m by n and then replace the Aij by Aijb. So, then we get this MP times NQ dimension matrix. So, how this Aijb is defined? So, this Aijb is defined to be, you take the matrix B and then just multiply each entry of this matrix B by Aij. So, you take this Aij and then multiply by B11 like that, Aij multiply by B1Q etc. Aij BP1 etc. Aij BPQ. So, you are just multiplying each entry of capital B with Aij. So, that is how this Kronecker product is defined. So, indeed what one can prove that if you actually starting with two linear operators f and g, the matrix of this f tensor G with respect to the natural tensor product basis. So, that is going to be exactly looking like this Kronecker product. So, this is actually some important fact. So, let me just verify. So, let us fix as before some of the maps. So, let us say f is from U to V and we just assume that the dimension of U is n and the dimension of V, okay, let me call it V here. So, the dimension of V is m and the map G is given from W to Z, where W let us say has dimension Q and then this as dimension P. So, basically the matrix of F with respect to the basis of U and V is going to have dimension m by n. So, this is m by n matrix. So, we just denote it by Aij, and similarly the matrix of G with respect to some basis of W and Z. So, that is going to be P by Q matrix. So, which is exactly given by BLK. So, then we want to say that the tensor product with respect to the tensor product of respective bases. So, that is going to be exactly the Kronecker product of the corresponding matrices. So, this is the result that we want to prove. Okay. So, for that purpose, so let us actually fix some notation. Let us call u1 etcetera un to be the basis of u and v1 etcetera vm. So, this is basis of v. Similarly, w1 etcetera wq and then z1 etcetera zp. So, these are basis of w and basis of z. So, this is the notation that I am using. So, now how this matrix Aij is defined? The matrix Aij defined as follows. If I look at f of uj, so this is exactly given by summation Aij vi, where I ranging from 1 to m. So, then you just simply write down the jth column as A1j etcetera AMJ. So, this is how the matrix, the jth column of the matrix bracket F is defined. Okay. If we use that, so you can see that so since u1 etcetera un is a basis of u, v1 etcetera vm is basis of v. So, we get this ui tensor vj. So, this is indeed basis of u tensor v, and the size of this is going to be mn, actually mn number of elements. So, I indeed varies over I 1 to n and j varies over 1 to m. Similarly, we have a basis so which is given by so actually we are going to look at So, let us look at the tensor product where it is defined. So, f is defined from u to v and then g is defined from w to z. So, f tensor g is defined from u tensor w2 to v tensor z. So, we have to take corresponding basis here. So, which will be given by uj tensor wk, and similarly here the corresponding basis is going to be equal to vi tensor zl and ijkl, they are all like running over respective sets. So, now let us actually look at how the tensor product is defined. So, let us fix this notation. F of uj is going to be exactly equal to summation aij vi, I ranging from 1 to m, and similarly g of wk is going to be exactly summation blk zl, l ranging from 1 to p. So, this is by definition. Now, if you look at f tensor g, which is applied on uj tensor wk. So, this is going to be exactly f of uj tensor g of wk. So, we need to just see how f tensor g act on the basis. So, that is what we are actually calculating. So, this is going to be exactly equal to summation aij vi tensor summation blk zl, and now using the linearity in both variables. So, if we just rewrite this, so this is going to be exactly equal to summation aij blk vi tensor zl. So, you can see that. So, what should be the entry of the corresponding this ILKJ position. So, here the I actually runs over from 1 to m and j runs over from L runs over from 1 to p, and we have computed the action of f tensor g on this basis vector uj tensor wk as this. maybe let me do one example. For example, we can actually look at F tensor G and then apply it on U1 tensor W1. So, then you can see that this is exactly equal to summation I range from 1 to m and L range from 1 to p A I 1 B L 1 V I tensor Z L. So, now if we take these coefficients and then list them using the natural order, you can see that this is going to be A 1 1 B 1 and A 1 1 B 2 1 etc. A M 1 B 1 1 and then etc. A M 1 B P 1. So, this is nothing but the first column of A tensor B, where A is the matrix F and then B is the matrix G. Okay. So, this actually tells us that what should be the correct matrix. So, this proves indeed the matrix of F tensor G is exactly the product of the matrix of F and matrix of G, the Kronecker product. Okay. So, using this we can actually conclude more about the traces and so on. Maybe I will do it in the next class. I will stop here. So, using this we will be able to actually make some observations about traces which will be used to compute the characters on the tensor products. So, maybe I will do it in the next class. I will stop here. Thanks.